This is Lab 6, which is associated with Lecture 6. And Lecture 6 was a bit long today, so we're just going to take about 10 minutes to go through some code to talk about some of the concepts related to Lecture 6. And the main concept I want to talk about is I want to revisit what we talked about at the beginning of that lecture, where we talked about training sets, validation sets, and testing sets. And I wanted to use the previous code from Lab 5 to demonstrate this, okay? So previously we had been working with K&N regression, so we can load that up with under the FNN library, and we had generated this data. It was just some uniform data, some x's between -1 and 1, and then we squared them, added a little bit of noise, and called that y. So if we plot those against each other, this would be our data, say x against y. And what we had done last time is we had split it into testing and training, and maybe we should really call this validation and training. And but this is similar to last time, except I've renamed the test data set, I've renamed it the validation data set, which is probably a better name for it, although people are pretty sloppy all over the place in the machine learning world with mixing up training and training data and validation. Testing data and validation data. And so what we did is we split our data into a training set, and we're going to split it into a validation set. And then we pulled off the various constituents, training x's, validation x's, training y's, and validation y's. We had written this function that fit our K&N regression model, passed in the training x's and the training y's, passed in a value of k, which we could supply to the function, and then it's going to predict it on whatever we want, and it's going to evaluate those predictions against the x and y that we give it, okay? And what we had done is we had tried out a whole sequence of values of k, so kseq is our sequence of values of k, and we had said, okay, we're going to try out all this sequence, and we're going to evaluate how well this does. And so we had done this, and we had then calculated their training RSSs for the various values of k. And I guess we can put this line, nope, not that many lines. Let's put this up here, right? So, come on, Jupyter, undo. Okay, I want that code, and I want to put it here. There we go. So, right. So what we're doing is we're just going to apply this evaluate function over our k sequences. And in the first case, we're going to evaluate the training data and looking at the training RSS. And we could make this, say, if you wanted to make this MSE, you would just change sum to mean. I'll leave it as was. It doesn't really matter, right? And you can also do this on our validation data, passing it into validation data and evaluating those models, right? So we run that, and we could plot those against each other, right? So here, my red is my training errors, and my black points are going to be my validation metric, right? So we get a gorgeous curve like this, which looks pretty nice. It shows that, generally speaking, the black points, which is the validation, typically are above the red points. Not always. We see in the tail here, we kind of have things flipped. We'll rerun the code at the end, and we'll see that that's not always true. But what's important is that if I evaluated on my training data only, and I had picked the value of k, it would have told me just to choose k is equal to 0, because that would give me a training RSS of exactly 0. We talked about that last time. Nonetheless, we see this really gorgeous curve here, right, where there is some minimum, and this is basically hopefully helping us navigate that variance bias trade-off, right? Because in the training data, it's just telling us to choose the most flexible model as possible, which is going to have to, we know that if we go too flexible, we see the test or the validation errors start to increase because we increase the variance too much. If we think about it in a bias variance trade-off. So we see if we can, when we look at the testing, or the validation, people use validation and testing in all sorts of ways. So it's, let's see if I can get it right. So this is the validation, we're calling it now. There is a minimum, and it somewhere around, I don't know, 5 or so seems to be the minimum value for K that we can choose, right? We could actually ask that. In this case, it's going to be 5, right? So that's all good, and that's a totally reasonable way of building the model. Just like minimizing, for a regression, we effectively minimize the training RSS. That's how you choose beta hat in a regression, right? But you don't want to take that training RSS as a metric of how well it will perform on new data, because you don't know how overfit it is. Maybe it's overfit, maybe it's not, but maybe it is. You just don't know because it's not independent set of data. And same with this, it's very reasonable to optimize over what we call like a hyperparameter, say K. Reasonable thing to do. You just don't want to interpret that, the training, that the value of this black point here, which seems to be about K is equal to 5 or so, right? So that's, by this procedure, it's a reasonable thing to say, okay, we should build our model based on that. But you don't want to take too seriously that the value looks to be like 1 point something here for our validation metric, because we've minimized the validation metric, so it's going to be overly optimistic, which we talked about at length. So if I rerun this chunk here, it's about 1.5 is our validation metric. What we could do is we could, instead of our training and our validation set, we could generate, in this case, the data is generated. In reality, you'd cleave off, but just to prove my point, if I were to generate what I'm calling test X and test Y, which is just regenerating some other data, right? I guess this should be 50 by 1, right? And I'm going to fit my model, I'll train it on the training data, and I'm going to evaluate it on my now independent test data set. So this test data set is different than the validation data set, in that the validation data set was used to choose the value of K. The test data set, in this case, because we've literally just generated it, in reality, you would split your data in, 3 parts or something. But it will be an independent evaluation of how well it does. So we predict on this independent set, and then we evaluate it. Using, this is going to give us my RSS. This last line is my RSS. So you can see here that my validation RSS is actually lower than an RSS I would get by using that model on an independent set of data, right? So the validation RSS is overly optimistic for what the error is actually. So again, it's reasonable to optimize a hyperparameter. It's just don't take too seriously, if you do that optimization, the validation RSS at that really highly fine-tuned hyperparameter, right? What you really want is another independent set of data, a test set. And the reason is because in this case, as we show, if we generate an independent set of data, we actually get a higher error on independent data. And so this validation RSS is overly optimistic. Okay. Now this is just one example. We could run this piece of code up here a bunch of times. We're just going to replicate it, say 100 times. We apply a little histogram of the RSSs, and you look, we actually got real lucky. The RSS is on my independent set of data. So this is just generating an independent set of data and evaluating the RSS. Those RSSs tend to be really large. They tend to be close to having a 1.5. So that is a really overly optimistic estimate of if we were to use this validation It's way overly optimistic. Now this is one particular example. We could just rerun all this. Let's just restart the kernel and run all the cells again. So re-randomize everything. Okay. Let's see how this pans out. We could just see, a couple different randomizations here. Hopefully this is going to work. Well, it's going to take its sweet time restarting, isn't it? We sit and wait. Well, the point being, I mean, I guess this histogram at the end showed it well enough anyways. And now the histogram's disappeared, so isn't that nice? But the point being is that it was overly optimistic. Okay, so this should have restarted now. Let's just let's run all the cells. Do a re-randomization just to see this one more time. All right, so again, nice little curve. Different curve, but my black points here are my validation. Has a nice curve. Again, my training data tells me to choose k is equal to 0. In this case, my optimal is 7. It says my minimum validation at that value of 7, right? So that is 2.12. Is that what it says? Yeah. So something like here, that seems about 2.1. And again, if I do generate one new data set, I'll actually get on an independent data set, I get a higher error. And again, you see that we tend to get pretty high errors here. Let's see if we can just do this one more time. Let's just restart. Okay, and just rerun all the cells. All right, here's our data. Now this is the picture, the realized picture, right? So we see that how optimistic these red points are, right? The red points are the training ones. So optimistic in this case. The testing data or the validation data set always at each value has a higher thing, has a higher metric, a worse RSS. The minimum seems to be about 5 again. It is. My validation says it's about 2. But again, always, every time I run this, right, it's so overly optimistic. If I evaluate an independent set of data, we get such worse, higher metric, right? So this is to say, just be careful. And this is why we do a training, validation, and test split if you need to optimize over this kind of hyperparameters. Okay, but that's, I think, a nice illustration, and we'll stop there.